Good afternoon, everybody. Hope you're all healthy and safe at home. So let us continue with our session. In the last section, we had discussed about Banach spaces and did various examples of Banach spaces. So in this section, we are going to move on to a theorem which tells us about, it is called as a completion theorem. So let's see what the theorem states. Theorem 1.5.5. So the theorem states that let E be a normed linear space. There exists a complete normed space E cap and a linear operator T from E to E cap such that first one is norm Tx is equal to norm x for all x belongs to E, and the second thing is that image of T is a dense set in E cap. So what is the theorem? Let's read it again. If E is a normed linear space, then we can always find a complete normed space E cap and a linear operator T from E to E cap such that it is isometric, that is norm Tx is equal to norm x, and the image of T is dense in E cap. Now just before this theorem, you can see the definition of isometry. It is just that if E and F are two normed spaces and there is a mapping from E to F, and we say that that mapping T is isometry if norm Tx is equal to norm x F. Norm Tx F is equal to norm x E. That is, here norm F and norm E are different norms. One is a norm defined in E and the other is a norm defined in F. So we say that a linear mapping T from E to F is isometric if norm F Tx is equal to norm E x. So I hope it's clear. So let us see how we can prove this theorem, theorem 1.5.5. So let's first of all write down what all are given to us. That is, E is a normed space. Then we have to show that there exists a linear map T from E to E cap, and we need to show E cap must be complete. Also, norm E cap should be equal to norm E x, where x belongs to E, and image of T is dense in E cap. So these are the things that we have to show. We are given that E is a norm space. We need to show there is a linear map from E to E cap, where E cap is complete space, complete norm space, and also this linear map T, it is norm preserving isometry, it is an isometry, and the image of T is dense in E cap. So let us see how we can do this. First, let script T be the space of all Cauchy sequence in the given normed space E. So let us consider a sequence. Let x cap belongs to script T. Then what can we say? This sequence x cap would be Cauchy's, right? Now we had done properties of Cauchy's, that is, if a sequence is Cauchy, then the limit of that sequence will exist. So we can say that limit I tends to infinity norm xi exists because x cap is Cauchy's and x cap is given by xi. We know that they are infinite tuples, so 1 to infinity. So we know that the limit of this particular sequence exists. Now with the help of this limiting value, we are going to define a function. Okay, define P from the script E to R such that P of X cap, that is any Cauchy sequence, will be actually the limit of that Cauchy sequence. So this is well defined because every Cauchy sequence is, for every Cauchy sequence the limit exists, so this function is well defined. Now we can see that we can see that this P, the function, actually forms a semi-norm. That is, it satisfies the properties of a semi-norm. Okay, you can verify that. I'm not showing it here. It is easy, you just have to show the three properties. First is P of X is greater than or equal to 0. The second one is P of lambda into X bar is equal to lambda into P of X bar, and the third one is triangular inequality. So you just have to check whether these P satisfies all the properties of a semi-norm. Now what we are going to do is we are going to define an N, a set such that it consists of all X bar sequences, Cauchy sequences belonging to script E, such that P of X bar is 0. So what does it actually mean? N is the collection of all sequences whose limiting value is 0. That is, it is a collection of all sequences which converges to 0. And the sequences has a speciality, that is, they are all Cauchy sequence. So it is a collection of all Cauchy sequence which converge to 0. Now from the definition of N itself, we can easily see that N is clearly a closed set, right? Now because if we take any Cauchy sequence, it will converge to point 0, and 0 is an element of N itself. So any Cauchy sequence, a limit exists in N itself, therefore it forms a closed set. Now we have a set of Cauchy sequence, that is script T, and a closed set. Using these we are going to form a quotient space. Now for that we are defining E cap to be script E by N. Okay, this is a quotient space, and we had seen that while defining semi-norm, that semi-norm actually forms a norm for the quotient space. So we have got a quotient space, and P of X bar equal to limit norm Xi forms a norm in it. So we have a space, quotient space, script T by N, and the norm given by the semi-norm. Also note that we had seen that in such cases, the coset is nothing other than P of X bar itself. This is how we had seen in the definition of the semi-norm, and as the semi-norm forms a norm for the quotient space, we have a quotient norm space with us. So now let us define the map T from E to E cap by P of X is equal to the space or the quotient coset X bar, where X bar is nothing other than the constant sequence X, 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 etc. Okay, I hope it's clear. We are defining a mapping T from E to E bar by P of X is equal to the coset X bar, where X bar is this constant sequence XXX. Now this X bar is a constant sequence. Now since it is a constant sequence, we can say that this is Cauchy's, right? X bar is Cauchy's, and so X bar belongs to the script E, space of all Cauchy sequence. So that is, and also we have P of X bar is equal to, by definition it was limit I tends to infinity norm of Xi, right? Now what is the specialty of x bar? X bar is a constant sequence x. So this is none other than limit I tending to infinity norm of x, because each coordinate terms is x itself. And what will be the limit of this value? It is nothing other than the constant norm x itself, right? And what was p of x bar? P was the quotient norm on e cap, right? So norm of tx will be p of x bar, right? Why? Tx will be an element in e cap, and any element in e cap will be of the form of cosets, and so norm of tx is nothing other than p of x bar, or you can write it as coset x bar. Okay, but we know that p of coset x bar is nothing other than p of x bar, and we have seen that p of x bar is norm x itself. So what did we get? We got norm tx is equal to norm x. So the mapping that we defined is a isometric mapping. Okay, so next what we have to prove? We have to prove that we have to prove two things. That is, one is e cap is complete, the space that the quotient space that we defined, and the other thing was image of T is dense in E cap. So first we are going to show that image of T is dense in E cap. Okay, for that let x cap equal to xn be a element of script T. Now since x cap is an element of script T, what we can say? We can say that this sequence is Cauchy's, right? So for every, by definition of Cauchy sequence, for every epsilon greater than 0, there exists a capital N belongs to a set of natural numbers such that the norm of xn minus xm is less than epsilon for every n comma m greater than n. Next, we are going to define a constant sequence by xn bar, which is equal to the constant sequence xn, 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 and so on. Okay. Then since xn bar is a Cauchy sequence, we can say that this xn bar belongs to script T. Because it is a constant sequence, it will be Cauchy's, hence it belongs to script T. Now, so by definition of the linear isometry, we have T of xn will be none other than xn bar. This is how we had defined our linear map. Now, let us see. P of xn bar minus x bar. This is none other than P of xn bar minus x bar. This is by the definition of the semi-norm. Now, since this is P of xn bar minus x bar, what will this value be? This will be less than epsilon. Why? X bar was nothing other than the sequence xn, and xn bar is the sequence xn, constant sequence xn, 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 xn. So this will definitely, that is P of xn bar minus x bar will be definitely less than epsilon. So this implies every element coset x bar which belongs to E cap, okay, it will be, we can find an sequence belonging to script E such that P of x bar minus Txn is less than epsilon. That is, Txn is none other than xn bar. So we have done that P of xn bar minus x bar is less than epsilon. So for every coset x bar belonging to E cap, we can find an element xn belong to script t such that the distance between txn, that is cos at xn bar, and the cos at x bar is always less than epsilon. So we can always find elements in the image of t which is lying close to the element in E cap. So from this what can we conclude? We can conclude that image of t is dense in E cap, right? We took an element x cap, cos at x cap, x bar in E cap, and we saw that the norm which is defined, norm P of cos at x bar minus Txn. Now this Txn is an element in the image of T, and that is always less than epsilon. That is, image of T is dense in E cap. So I hope it is clear, this portion, that is, we had shown that image of T is dense in E cap. Now next what we have to prove? We have to prove that E cap is complete. So to show that E cap is complete, what must we show? We must show that if we take any Cauchy sequence in E cap, then we have to prove that that sequence is convergent. So let us consider a Cauchy sequence. Let cos at xn cap be Cauchys in E cap. Then by definition, for every epsilon greater than 0, there exists a capital N belonging to set of natural numbers such that P of cos at xn cap minus xm bar is less than epsilon for every n comma m greater than n. Because we had defined a semi-norm P for the quotient space E cap. So since xn bar, cos at xn bar is Cauchy's in E cap, we can say that P of cos at xn bar minus cos at xn bar is always less than epsilon for every n comma m greater than n. Now let us define a few things. That is, let us consider epsilon n to be greater than 0 such that it converges to 0 as n tends to infinity, and choose an element xn belongs to E such that P of cos at xn bar minus Txn is less than epsilon n. Now we can do this. Why? Because we had shown just before that image of T is always dense in E cap. So correspondingly we are choosing an epsilon n and an xn such that P of cos at xn bar minus Txn is less than epsilon n. Now we will show that this xn that we had chosen in epsilon is another Cauchy sequence. That is, to show that it is Cauchy's, we have to show that norm xn minus xm is less than epsilon for every epsilon greater than 0 and n comma m greater than n. Right? Now we can write this as norm xn minus xm is nothing other than P of Txn minus Txm. Why? Because we had shown that T is isometric. Okay. So we have norm of xn minus xm is equal to P of Txn minus xm. What we are going to do is we are going to add and subtract a few terms, that is Txn minus cos at xn bar plus cos at xn bar minus cos at xm bar plus cos at xm bar and minus Txm. Now the property of the semi-norm, we can using triangle inequality, we can write this as P of Txn minus cos at xn bar plus P of cos at xn bar minus cos at xm bar plus P of cos at xm bar minus Txm. Now we had shown that this is less than epsilon n, this would be less than epsilon m, and this we had chosen the Cauchy sequence, so this will also be less than some epsilon. So altogether we can see that this tends to 0 as n greater than equal to m tends to infinity. Okay, so what have we seen? We have seen that for every epsilon greater than 0 there exists an n such that norm xn minus xm tends to 0 for every n comma m, n is greater than m tends to infinity. So this implies xn is Cauchy's. So once we have a Cauchy sequence, we can say that it is an element of script T, right? So next what we are going to do is we are going to say that any sequence that we had chosen, that is a sequence xn cap, which was an element of E cap, we are going to show that this converges to this particular sequence. So let us denote the sequence Cauchy sequence xn by x dot cap, right? Then what can we say? P of xn cap minus x dot cap is none other than P of xn cap minus, we are adding and subtracting txn plus T of xn minus x dot cap. Okay, and by property of norm we have P of xn cap cosec xn cap minus txn plus P of txn minus x dot bar. Now we know that this is tending to 0 also, txn, and x dot cap, x dot bar is none other than, actually it is xn bar itself. So we have this also tends to 0. So what do we get? The distance between xn bar and x dot bar is tending to 0. So we can say that xn bar, coset xn bar, it converges to, so P of coset xn bar and coset x dot bar tends to 0. So this implies coset xn bar converges to coset x dot bar. So we chose an arbitrary sequence xn bar belonging to the quotient space E cap, and we proved that this was chosen to be Cauchy's, and we proved that it is convergent. So since xn bar, coset xn bar was an arbitrary sequence chosen, we can say that this result holds for every sequence in E cap. So every Cauchy sequence is convergent, and thus we have proved that E cap is a complete normed space. So I hope the theorem is clear for you. So we have proved that the space that we had defined, the quotient space that we had defined, is a norm space, and we show that the mapping is isometric, and also we show that the image is dense in this particular quotient space. So I want you guys to just go through the theorem or read it once or twice again to make the concept clear. So that's it for today's class. I hope you guys will understand the theorem properly. Just read it a few more times, then I'm sure that you'll understand it. And that's it. So stay home, stay safe. Thank you.